Hi, I thought I'd start this lesson with a photograph of one of my favourite places in the world. This is the Isle of Harris. In particular, it's one of the most spectacular beaches in the country called Luscantire. The reason I've shown you this is that this whole landscape is made of high grade, regionally metamorphosed rocks, ancient lumps of the continental crust that have survived through some fairly extreme metamorphism to create the spectacular landscape we can find in the far, far northwest of Scotland. Anyway, what I want to do in this lesson is work through the putting it all together activities. So we're working on pages 9 and 10 of our Theme 6 booklet. Okay, let's go. Question 6 then uses these two polished specimens of metamorphic rocks. Notice they're both the same scale, but their textures and their mineralogies are very, very different. Read through the questions carefully and have a go answering those questions about those two rocks. If we turn the page onto page 10, question 7 then relates to this photograph. So this is showing again another picture of a polished surface of a metamorphic rock. You can see there's a 1 cent coin. It's about the same size as a 1p coin there for scale. We've also got the scale bar to give us a clue as well. Have a go at those questions about that particular photograph as well. Okay. Remember that both of these questions are all about tying together what we've already learned through the rest of this theme. So, press pause now and have a go at those questions. See what you come up with. Okay then, let's see what you've found. So question 6a asks you to describe two differences in texture between these two rocks. Rock A is foliated. We can see that there's a clear alignment of the mica crystals in this rock. It means it's foliated. The other crystals don't seem to show it quite so much, but it's the mica that's the key mineral there. In rock B, there's no foliation. Those grains are just fused together. Now, the second difference in texture, we could use the proper geological terms. So rock A is porphyroblastic, rock B is granoblastic, or you could just describe the difference. In rock A, we have a large, coarse garnet crystal that's grown within the rock during metamorphism, and then we've got finer grain crystals surrounding that. In the granoblastic texture that we see in rock B, all the crystals in this rock are approximately the same size. Question B then, just related to rock B. You're told that rock B will react with dilute hydrochloric acid. So if it's going to fizz, the mineral that it's made of must be calcite. And if we've got calcite as the mineral within the rock, its parent rock material, what we originally started with, must be a limestone. For question C then, we're asked to complete this table. So rock A is a schist. We can tell that because of these sheets of mica, schistosity that runs through that rock. So the temperature it formed at was high. The pressure it formed at was also high because it's foliated. We know it's high temperature because we've got recrystallization, we've got the growth of garnet, and we know it's high pressure because of that foliation. Now, high pressure, high temperature metamorphism is going to be regional metamorphism. Rock A has been buried deep in the crust. Rock B then is a marble. We know it's a marble because it's made of calcite. The temperature at which this forms then is high because we've got recrystallization going on. These grains are fused with each other. The pressure, though, is low because we haven't got foliation. There's no preferred orientation to the crystals we find in that rock. Now, high temperature, low pressure metamorphism is contact or thermal metamorphism. If we look at question 7 then, we have our photograph of this polished surface. So the pressure that formed this rock is going to be very high pressure. Two features that tell us this are that it's foliated, and that foliation has been deformed, it's been folded or bent. Okay, so there's a huge amount of pressure acting on this rock. It formed at a high temperature, and the reason we know that is because the rock has bent easily. It's deformed, in quite a plastic way. We'll talk more about this in theme 13. You could also put the fact that the rock here has been completely recrystallized, although it's hard to see it from this photograph. And the metamorphic rock, you could call it a gneiss. You might call it a schist, but I think this one is probably more likely to be a gneiss because we've got bands of the different coloured minerals. Finally then, we were asked about the other event that's happened, and what we have is the intrusion of a small dike or mineral vein running through this rock. It's only a few centimetres wide, but that clearly has come along after the metamorphism because it hasn't been deformed by or during metamorphism. So, to summarise, we know that metamorphic rocks are formed at either heat and or pressure, some combination of those two agents, over a period of time. The composition we find in the metamorphic rock depends largely on what the original parent rock was made of. The heat can have an effect as well, but only to a small degree. What heat does is it causes crystals to grow. Where we have lots of pressure, we get foliations. Where we don't have much pressure, we get this non-foliated texture. And some minerals, particularly clay minerals, change a lot more easily than others. Okay, as we watch the sunset over Luscantire Beach, we've now completed, if like, all the theory about that we need for metamorphic rocks. What we need to do next time is just have a go at the homework activities and finish off the Theme 6 booklet. But that's for the second part of the lesson. I'll see you then.